Oh, hi there, everyone. Thank you for showing up for your learning. Great to start a class together with a nice lesson, isn't it? We've actually a little deep into the class already, but a very useful learning opportunity, I hope, learning activity. And we're going to be doing a lot more graphing with these little whiteboards, so do try and keep them tidy for the other groups and for yourselves in the future. All right, today we're looking at these things called exponential expressions. These are exponential equations that we're going to learn how to solve today. And the variable that we're looking to solve is up there in the exponent. Oh my goodness, I'm not used to solving things where the variable is up in the exponent. So let's take a look at when these questions are well designed and set up for you to answer them in this manner. You can use this manner to solve them. And you can think of this as an important learning step on the way to a very robust technique you'll learn next year for solving these types of equations. Not this year, though, next year. So you want me to solve these ones, show you how to do it? Or just go in, we'll do the lesson, we'll come back to these two. Let's come back to these two after I've talked about them. Okay. So if you want to solve when the variable is in the exponent, you can create the same base on both sides. If the bases are equal, then the exponents must be equal. So that's the main thing that we're going to be looking for today, is to create a common base there. And we're going to be doing that by changing the bases. I was actually showing this to you over there already with, I did some base changing. Wait, was it over there? Yeah, it was when I was talking about how we know 2 to the 6 is 64, because it's the same thing as 8 squared. Why is 2 to the 6 64 and 8 to the 2 64? Stay tuned. You'll see. You are also going to be building on what we looked at yesterday, particularly the power of a power law, where x to the a to the b is equal to x to the ab. And we'll also be applying the distributive property. Remember that if I multiply a monomial by a binomial, that will create this Mario jumping on both Goombas situation, where you get a times b plus a times c. So let's go. Changing the base. So, I forgot to erase those. If you wanted to write a 9 and 27 as the same as exponents with the same base, you would need to notice that they're both powers of 3. And here, you notice that I do these little tricks, right? Like I'm like, okay, 3, 9, 27, 81, 243, so there'll be 729, okay? And then you can count your powers on your fingers to start recognizing these. Powers of 2, 3, 4, and 5 are good to have in your mind. They're the kinds of ones that I'll use on a test. But if you want to get ready for math contests and to build your math muscles, knowing the bigger numbers and knowing the charts up a little higher is also helpful. Or at least being able to say, they might be, and then knowing to test on your calculator. So 9 is 3 squared, and 27 is 3 to the 3. If I didn't know that, what I could do is I could say, well, clearly they're not powers of 2. Perhaps they're powers of 3. And then on my calculator, I can just do 9 divided by 3 and find that's 3, and then say, oh, okay, then 9 equals 3 times 3, or 3 squared. And then I might say, well, let's test 27 for the same thing. Divide it by 3, and we get to 9, and then you're like, oh, I see where this is going. Yeah, 27 was a power of 3 as well. You can use a calculator to test these if you don't have the lists memorized. Does that make sense? So just like yesterday, I want to make sure that when you forget that 27 is a power of 3, you can confirm with a calculator or some method on a test to recognize that yourself. 42 and 4 and 32, you might think, well, 32 is 4 times 8, so maybe it's a power of 4, but unfortunately it's not. 4 will miss 32. 4 goes 4, 16, 64, so it jumps over 32. But they can both be expressed as powers of 2. So 4 is 2 squared, and 32 is 2 to the 5. So let's keep going. All right, if I told you that 2 raised to the power x gave me 256, that's like saying on your graph, there was some x value out here somewhere where this graph that you made of 2 to the x went up to the value 256. Okay. You didn't have that much space on your graph unless you set the scale in a really funky way, but there you go. So what is x? Anyone know this one? Count, Akriti?
Is it 8?
It is indeed 8. So what I will do here is I will change the base. So 2 to the x is equal to 256. Copy it out. Oh, you don't need to copy it out. You already got this there. And then you're going to write 256 in a new way. 2 to the x is equal to 2 raised to the power 8. There you go. How would I test that on a calculator if I didn't have Akriti's fast math prowesses? I go 258. Wait, is that what I had? No, 256. And I'm suspicious it's divisible by 2, so I do this. Divide by 2 equals. Okay, that's once I divided by 2. Divide by 2 equals. That's twice I divided by 2. Divide by 2 equals. Can I just do equals? Yes. So that's 3 times, 4 times, 5 times, 6 times, 7 times, 8 times to get down to 1. So it's 2 to the 8. You have to get all the way down to 1 if you want to use this method to test for what power of 2 is that. People see how I did that method? Cool. Ali?
Is that just using like guess and check?
Yeah. Yeah. It would also be like, I recognize that this is a question given by a math teacher who wants me to use the changing the base property. I expect that 256 is therefore a power of 2. Let's use my calculator to find out which power of 2 it is. Malcolm?
Is that like fully simplified right there?
No.
You have to put like divide the 2 out?
No, you don't divide the 2 out. I know that if 2 to the x is equal to 2 to the 8, I just say, well, then x must be 8. Yeah, it's not really a mathematical operation, and it's certainly not achieved by dividing by 2. Okay? So it's just if the bases are the same, then the exponents must be the same if they're equal. Agreed?
Could you just like make a factor tree to like solve for this?
Yeah, you could as well. Yeah, you could also factor tree it. That's the same thing as testing it on your calculator. So 256, factor trees 2 and 128, factor trees 2 and 64, factor trees 2 and 32, factor trees 2 and 16, and oh, I recognize 16, that's 2 to the 4. Maybe you recognize 16 as 2 to the 4, so you got 2 to the 4, to the 5, to the 6, to the 7, to the 8. So it's another way you can do it. And I would prefer doing it that way, agree. That's better than just testing it on your calculator, because people are going to get 2 to the 7. They're going to go, oh, I divided it by 2 7 times. I got to 2. It's 2 to the 7. Now, there's still 1 2 left there. You need to get all the way down to 1. So, yeah, I like factor tree better. But I want to give you multiple different methods if you don't recognize it. Now, what about this little beastie? Okay. We have 32 to the x minus 1 is equal to 4 to the x plus 2. There is some value of x that makes this equation true. Let's find it. So here's how I do it. First, I'm going to rewrite 32 as a power of 2. This is 2 to the power 5. That's 32. And it's raised to the x minus 1. And that's equal to 4. 4 is a power of 2. What's that? 2 squared. So I'm going to rewrite 4 as 2 squared. And then I'm going to write that as x plus 2. Okay? All right, now we've got them with the same base. But we've got powers of a power on both sides. So let's resolve our powers of a power first. We know that here I'm going to be multiplying this in. Let me just get a nice color here and zoom in. So I'm going to use the distributive property here because I'm going to be multiplying 5 times x minus 1. Because when I raise, remember that x to the a to the b is equal to the x to the a multiplied by b. So I'm going to multiply 5 by x minus 1. To do that, I do 5x minus 5. Over here, I will do 2x plus 4 by applying the distributive property. So let's see our next line. This could be 2 to the 5x minus 5. And this is 2 to the 2x plus 4. Apply the distributive property and the power of a power law. Okay? Now, here, Malcolm, you see, like, if 2 raised to some exponent is equal to 2 raised to some different looking exponent, those two different looking exponents must be equivalent. Okay? It's not really a mathematical operation I'm doing to take that 2 out. It's more of a logical step. You see? So it's not really like an inverse operation here. Sorry?
The 2 and the 2 are equal.
Yeah, the 2 and the 2 are equal. So you could think of it as canceling each other out, but that sounds a lot like canceling by division to me, and that's not what this is. Okay. The inverse operation does exist. You'll learn about it in grade 12. I'm happy to chat about it, but you don't need it right now. You just need to know here at this point, therefore 5x minus 5 will equal 2x plus 4. That's all. And then we go ahead and solve. Get out your inverse operations pen. Minus 2x from both sides. And let's add 5 to both sides. See what we're going to get here? Yep. When we have something like this, if you have the same base raised to different exponents and they're equal, the different exponents must be the same. They're not canceling away. I didn't divide or subtract or multiply both sides. I just noticed, well, that must be equal to that. It's more of a logical step, like this raised to, watch here. If I write it this way, it will be simpler. If I have a 3 to the A equals 3 to the B, A equals B. It's just that. Okay. Notice I'm not saying I'm dividing by 3 or I'm subtracting 3 or something like that. It's just a logical conclusion based on this to some exponent I don't know yet is equal to this to some different exponent I don't know yet. Those two different things must be the same.
Why is it when you like subtract -5 and add -5 or add 5? Why would it get you a different answer?
Where? What? Sorry, which one? You said if I added 5 or
the other way around?
Which one? Oh, like if I, instead of subtracting 2x, and I could subtract 5x?
Yeah.
Like, you have a sign error then.
Yeah.
It will give you the same answer, but it's my way only has positive numbers. Your way will have negative numbers with a higher chance of a sign error. There you go. That's why. Yeah. Okay, so that's the process for a question like this. Let me zoom out so you can see the whole thing. Okay. Need a second there? Any questions about this one? Hannah? Sure. I think, let me see the next one. The next one is pretty tricky, but yeah, go ahead. It gets trickier. All right, sure. Ty? Yeah. Yeah. Yeah, see, I wanted all my x's on one side of the equation and all my numbers on the other side. So to resolve that, I said, well, I'm going to push the 2x this way because I know that'll leave me a positive 3x. And I'll push the negative 5 that way because that'll give me positive numbers. That way, I get positive numbers. If I do it the other way, I get the same numbers, but they're both negative. I don't want to do that. Okay, let's keep going. This one. Now we're going to solve for x given that 4 to the 2x minus 1 is equal to 1 over 64. Is 4 a power of... Do they have a common base that I can write them as? 4 and 1 over 64? Lily? 2 to the power negative 4? Almost. That'd be 1 over 16. A little more still. There you go. All right. So 1 over 64 can be written as 64 to the negative 1. You can think of this way. And then say, oh, 64. I can write that as a power of 2. But actually, I was kind of trick questioning you here. You can actually write it as a power of 4 as well. 4 quadruples to 16 quadruples to 64. So 64 is 4 to the 3. Okay? And why is it that 4 to the 3 is equal to 64, but 2 to the 6 is also equal to 64, and 8 to the 2 is equal to 64? Who can explain this for me? Why are all these different facts true? And they're essentially all the same fact. Because 4 here, 4 to the 3, could be written as 2 to the 2, which is 4, raised to the power 3, which is 2 to the 6. 8 to the 2 is the same thing as 2 to the 3 to the 2, which is equal to 2 to the 6. See the connections, Haley? No? Oh. I have this habit. Yesterday in period 3, they were like, where'd that 2 and that 3 come from? I was like, well, I'm this guy who's good at math, and I noticed that 6 is 2 times 3. Here, I have like 8 is the same thing as 2 to the 3. Sometimes working backwards. Like normally, you're used to saying 2 to the 3. I know that. That's 8. 2 times 2 times 2, 8. Right? But you can also work the other direction and then simplify things to like a common base that way. It's the same idea that we're using to solve these types of problems. So if 64 is 1 over 64, 64 to the negative 1, let's write 64 a new way as 4 to the 3. 4 to the 3 is the same thing as 64. And it's raised to the negative 1. So that's equal to 4 to the negative 3. 1 over 64 is 4 to the negative 3. You could check your calculator and it would tell you too. Now let's rewrite this as that. 4 to the 2x minus 1 is equal to 4 to the negative 3. And then we have this logic step here where I just remove the bases and equate the exponents. 2x minus 1 equals minus 3.
How are you finding the negative 1?
Which negative 1? Oh, here? Oh, because I remember that a negative exponent means flip that number.
Yeah, but why would you bring that into 4?
4 to the 3 here? Because 64, I rewrite 64 with the 4 as a base so that I can solve this problem because I have 4 as the base on the other side. So I know that 4 to the 3 is 64, so I can rewrite it there.
And then you have to bring it in the 1?
Hey, and then I just use my power of a power law to say 4 to the negative 3 is equal to 1 over 64.
Do you always have to bring in the 1? The negative 1?
If it's there, yeah, just simplify. I could have written this over here as 4 to the 3 to the negative 1, but I think that's awkward. Just simplify it. Yeah, there. So then I know that 2x minus 1 is equal to minus 3. So add 1 to both sides gives you 2x equals negative 2. And then divide both sides by 2 to find that x equals negative 1. There's our answer. Dun, 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 dun. Hi, Ellen.
So those like classes and stuff where you like add 1 to each side, or like you just need that like to get 3 from
If you spot it right away, then you just write it, yeah. Ella, I tend to look at your work in a couple situations on a test. When you have the wrong answer, I'll look in the work and then find as many marks for you as I can. Or if there's no work there and there's just an answer, then I might say, hey, show me how you did that on a whiteboard. And then if it's like, well, I take my phone, I point it at it, and I go to this cool app, and then I'm like, oh, okay, all right. And then we have another conversation. I'm not saying no, that's not happening here, but you would not be surprised that it does tend to happen in other classes that are less that have less personal responsibility for their academic work. Sorry? Oh, okay. So let's verify our answer. That's the best question today. But there's been a lot of great questions today. That's my favorite one. x is equal to minus 1, sub it in here and see if it's true. Okay? 2 times minus 1 is minus 2. Minus 1 is 4 to the minus 3. 4 to the minus 3 indeed does equal that. Because we figured that out over here to even solve the problem. Cool. Great question. So always check your answer after you get it. And this one we only found one variable, so it's quite quick to check. Keep going. Keep going. All right. Let's try this one. Yay, my favorite. This is why I was excited to get out of bed this morning, is do this example with all y'all. Okay, 1 over 64 and 1 over 8. I can't express 1 over 64 as a power of 4 anymore because 8 is not a power of 4. But they do still have a common base. What is it? 2. Good. So if I have to write 1 over 64 as a power of 2, what is it? 1 over 64 is equal to... Thank you. That's weird. That answer came in handy this time. We could have used it last time and converted everything to base 2, but keeping it in base 4 was simpler. Okay, so this is 2 to the negative 6, and 1 over 8. 1 over 8 equals 2 to the what? 2 to the negative 3. Good. So these are just identities, and we're going to use those identities to break this question apart. So 2 to the negative 6. That's good. I love the feeling of light bulbs turning on. That's great. Oscar?
Couldn't we just do the 8?
Oh, yeah, we could just use 8 as a base. Isn't that beautiful? Aren't we glad that we have Oscar here? So let's use 8 as a base instead. Oh, Lena, were you taking a note from me in pen? No, in pencil. Oh, good news. Okay, so 1 over 64 is equal to 8 to the what? 8 to the negative 2. Cool. Let's use that. So, and then 1 over 8, instead of writing that as 2 to the negative 3, let's write that as 8 to the negative 1. Good. It just flips it. So, let's go. This is 8 to the negative 2 multiplied by negative 24x plus 81 equals 8 to the negative 1 raised to the power negative 3x squared minus 3x. Okay? Now, at this point, when you get the question on the ropes like this, and it's just about ready to submit, you can simplify your exponents and write a new line, or you can just equate your exponents at this point and then do the distributive property. It doesn't matter when you do power of a power rule.
Oh, well, I get it now. So negative exponent going to fraction. So if it wasn't.
Sorry?
So negative exponent going to fraction. So if it was like 2 over negative 4, it would be 1 over 16.
2 over negative 4?
Yeah.
2 over negative 4? Well, that would just be negative 1/2 if it were a fraction. But and Oscar, there's another thing we could have done here is express that as a power of 1 over 8. But let's leave it this way. Okay. Yeah. Let's keep going. So now I know that negative 2 multiplied by negative 24x plus 81 is equal to negative 1 multiplied by 3x squared, but it's negative, minus 3x. So I'm just going to equate my exponents at this point. 8 to the this stuff is the same as 8 to the this stuff. There's the this stuff, and there's the this stuff. I just removed the base right away. So you have a choice, what I was saying here. I can do it where I multiply this in and keep it as an exponent, and multiply this in and keep it as an exponent. Or I can just write that stuff down, do the multiplication down here, rather than writing it as tiny little letters as the base. You want to see it the other way? Sure, I'll show you the other way. The other way looks like this, and you'll see that it is just the same. So this is 8 to the negative 2 to the, wait, this way. Chum, chum, chum. Just copying. Negative 24x plus 81 equals 8 to the negative 1, negative 3x squared minus 3x. Okay, and then I have another line here. 8 to the negative 2 times negative 24 is 48x. And negative 2 times 81 is negative 162 is equal to 8 to the negative 1 times those things. So that's 8 to the 3x squared. Just flip the signs, plus 3x. So I just did my power of a power law there. See what I did? Same as before. This just happens to be giving me a quadratic this time. My next line here will be 48x minus 162 is equal to 3x squared plus 3x. You can do it that way. If you like, if you have really good writing and your writing is good when it's small and in exponents up there, or you can do it my way here, which is this exact same thing. I'm just going to expand those. Here, this gives me 48x. And this gives me minus 162 is equal to 3x squared plus 3x. Same thing. These two lines are the same. It's just when do I remove the base? That's all. I just took the base out a line earlier here so that I have more space to work with. Okay, now let's solve. How do we solve something like that? Where I've got x's on both sides of the equal sign and one of them's even squared. I'm going to stand here and pretend I don't know what to do.
Minus 3x. And then you'll have the square root.
Okay, well, if I square root, then I'm going to end up with the square roots of x on this side, and that's going to be pretty awkward. As well, it's going to be the square root of a binomial, and that's going to be super awkward. Ty? 48x to the other side? Yeah, I like moving the 48x to the other side. Let's take everything to one side, everyone. Okay, so minus 48. Oops, that's the wrong place. Doesn't matter, but put it in the right place. So minus 48x plus 162, so that I get a quadratic that's equal to 0. 0 equals 3x squared. 3 minus 48 is minus 45x. And 162 is just 162. Okay? Starting to look a little more familiar? Yeah, we've solved these types of things before. It's not new. So here we go. Huh?
Can you do the equation? Like, can you do everything below the 48x minus 162, that equation below again?
Here? Okay, so I subtract 48x from 48x, and I add 162 to minus 162. That all adds up to 0. And then I have on the other side, 3x squared doesn't have any like terms to collect with, so it's still 3x squared. And then 3x minus 48x is minus 45x. And plus 0 here, plus 162 is just 162. So I just collected my like terms. This is I should have changed to my inverse operation pen. These are all inverse operations. In order to set the quadratic equal to 0, so that I can apply one of two of my favorite solving strategies. Solve by factoring or solve by negative b plus or minus the square root of b squared minus 4ac over 2a. We're not doing that today. Ain't nobody got time for that. Huh?
Why are you making it equal 0 just so you can factor?
Yeah, because now it's a quadratic, and there's values of x that are going to do this, and I want to find these values of x because those are my solutions. Right? The values of x that now satisfy this equation should solve the equation above because my algebra doesn't have any mistakes in it. So I see that all of these are divisible by 3, so let's divide both sides of the equation by 3. This is a little trick. When something's equal to 0, you can divide it away and don't need to keep it as a common factor, because even if I change the family of quadratic or the stretch factor, it's not going to change these roots. That's graphically why this is allowed. So I have 0 is equal to x squared, minus 45 over 3 is minus 15x, and then 162 over 3 is 54. Okay? And now let's solve. We got next game, folks. The next game to do. We want to multiply to 54 and add to negative 15. What two numbers multiply to 54 and add to negative 15?
-6, -9.
So x is equal to what? X minus 6 or x minus 9 is equal to 0. So that tells me that x is equal to 6 or 9. People know why the signs flip, right? Yeah? Yeah? Because this must be 0 or this must be 0. To make x minus 6 0, you make x 6, and 6 minus 6 is 0. Or if this one's 0, then x is 9, so 9 minus 9 is also 0. Cool. Doot, doodle, doot, doot, doot. There's some handouts. I give you some handout. 1 to 6. Oh, no, I created my own handout. Never mind. Quiz Monday, that's accurate. We'll quiz this topic and exponent laws on Monday. Tomorrow is a Delta Math day with only this topic and exponent laws. I also may give you a Desmos challenge tomorrow. Something like, I've been playing with this idea. I was playing with this last night about like the scale of cosmic objects. And exponentials are really useful for comparing the sizes of different objects. Like how many times would I need to double the Earth to get to the sun? If you take a look here, this is my x values and y values there are in kilometers. The blue ball is the Earth. What's the green ball? What's this? That's the moon.
Mars.
There's Mars. Isn't Mars small? Like Mars is so tiny. Yeah, this is Venus here.
Yes.
Venus is just very nearly the same size as the Earth, but not quite. The purple ball, Jupiter. Yes, that's Jupiter. That's our largest planet. And then the orange ball is the sun. Just look how much bigger the sun is than the Earth. So then I got playing with some exponential functions. This is an exponential function that goes between the top of the moon and the top of the Earth here. And then here's an exponential function that goes through the top of the Earth and the very tippy top of the sun up there. So you see just how much it has to grow to get to the size of the sun. It's just so much bigger. Yeah. So anyway, maybe I do something in here with Desmos where it's like, draw me some objects and I'll probably just get you some Delta Math practice tomorrow. Because we didn't get any practice on our practice problems on your sheet, which is too bad. But here's how we'll manage that. On Monday, I'll give you a little bit more time to work on this idea before we have a quiz. And then the new idea on Monday is exponential growth. I'll put in some practice problems into the Delta Math for tomorrow to get you started on the idea of exponential growth, which is really like the main area in our world where these ideas are going to show up. And with the last 5 minutes before, and then bye. Thanks for showing up your team learn at home.